Hello everybody. So today it's our lecture number 5. If you haven't watched the other lectures, I suggest you to go back to the others. This is the first lecture of Unit 2. And we're gonna talk about combinational logic. The idea now is that we're gonna understand how to put together the gates that we've seen and how that's gonna help us represent the functions and the behaviors that we want for our system. So there's two types of circuits that we can see in the digital world. That's combinational circuit and the sequential circuit. The combinational circuit, the output only depends on the current values that you have on the inputs. So it's a memoryless circuit. It's what's provided for the inputs that's gonna decide what you're gonna get on the output. And different from it, we have the sequential circuits, because on the sequential circuits, the output depends also in the current inputs, but also in the past results that you have from that circuit. So you have some memory, you have some feedback from the past into your circuit. But today we're only going to talk about combinational circuits. And in the future, this course also covers sequential circuits. So basically, what combinational circuits are based on this number or one or more inputs and a number of outputs. They are also called ports. And basically, what we need to describe this module here, this IC or this combinational logic circuit, it's what's the inputs, so how many inputs, which are the inputs, what we have for the outputs, which are the outputs, and a functional description that could be a truth table, or that could be a Boolean equation. And we also gonna need a timing description, because we're gonna see some delay from the inputs to the outputs. So usually you need to know what's the delay inside this circuit, so you can design your system over taking into account the delay that we have here. And as you can see, this idea of combinational circuit uses the idea of a black box. So you have this box, you don't actually have to know what's inside, but you know what's the behavior that this box is giving to you. So you have this level of abstraction. So you can have any type of modules here, any type of gates, but you know that depending on these inputs, you're gonna have these outputs. So one example here. So we have this combinational circuit here. We know that's a function y, and this function depends on a and b, in inputs a and b. And from the description of our circuit, we know that's an OR gate. So so it's A or B, and that defines the function, that defines the output that we need here. So in letter A, you see one implementation, can be just a regular OR gate, A or B, and you have your output Y. But you also can implement that with NOR gate. So that's a NOR gate complemented with a NOT gate, and you're gonna have the same equation, the same behavior. So you may ask, why you're using like two gates instead of one? It always depends on the devices that you have available, or in the type of design that you have, and the prices of the gates, or the prices of the IC that you're using. So that's really common. But the idea is, and we're gonna see that through the course, that you always can have a combinational logic circuit implemented in different ways and giving the same result. And also, if you always, it's better to reduce the number of gates. So sometimes you have a really complex equation here and you can simplify that using less gates. It's always a really good, even though you can use more gates and represent the same equation, it's always better to use less gates because it's cheaper. And yeah, so to define a combinational logic circuit, it's really important that it's composed of smaller combinational circuits. So all sub-circuits that we have here, for example, in talking about the level of abstraction again, so I can have this f1, it's just a function. I know that requires this input, and I'm gonna have this output, and that's all I have to know about this, and that could be part of a bigger circuit. So I have this abstraction, and after I have those guys inside here, I only care about this input and those outputs, and that's enough. So it's one level of abstraction. But if this is a combinational circuit, all the sub-circuits have to be should be combinational circuits as well. Otherwise you're gonna have feedbacks and you have to treat a different way. So you have to understand and to design in a different way. So you can see that all the wires here, or the wires comes from the inputs to the inputs of a sub-module or a sub-circuit, and the outputs goes or to the output or to another input. You cannot have wires coming back. That's a feedback, so there's no cyclic paths on the circuit to be a combinational circuit. And the wires are sometimes are called nodes. So that's gonna help you when you're seeing some examples on Verilog. That's called nodes. And so yeah, so all the wires has to come from the input to a gate output or a sub-circuit output input, and the outputs of this sub-circuit has to be to another sub-circuit input or to an output. So here we have some examples of combinational or wrong combinational circuits. So you can see in letter A, it's a combinational circuit. You have two gates, L1 and L2. You have node 1, node 2, and node 3. And you can see that comes from the input to node 1 or to logic gate 1. And you have the node 2 just connects the output of one gate to another one. And you can see that letter B, it's not a combinational circuit because you have the output from the exclusive OR here. It's connected the output back to the input of the gate. So this circuit here requires that you know the past value of the output to be included in the input again. So that's not a combinational circuit. This one is a combinational circuit. You have all the outputs here connected to inputs of another circuit, and you have the output. In this case, letter D, it's tricky because you can see that looks there's no feedback, but you can see that you have two outputs from module L3 and L4 connected to the same node to the input of another gate here. So you don't have consistent information here. So it's coming, the input of this gate, that's only one input, it's coming from two other gates. So that's wrong as well. That's not a combinational circuit. You don't have like a clear information here what's this input at a given time. So another clear combinational circuit, you have you can see a higher level of a combinational circuit. You cannot see the gates, but you know that this combinational circuit has two inputs and one output, and this output goes to an input of another combinational circuit, and probably these guys are the same, let's say, because they have the same symbol. Of course they don't have to be because they have two inputs, but it's really common that you develop a module and you use that module in several several times inside the same higher level circuit. And you can see letter F here is not a combinational circuit because you depend to know what's the output here to decide what's the next at a given time, you need to know the past. You need to know what's this output here to input here. So this is a sequential circuit as well. Yeah, so let's see how can some examples of, because the idea now, it's not every time that we're gonna have a truth table and it's pretty clear how we're gonna implement. Usually what we're gonna have, it's Boolean functions, and from those Boolean functions we can of course simplify them and have a different version with the same outputs. But this Boolean functions, it's gonna provide all the information that we need to build the digital circuit, the combinational circuit that we have. So okay, so let's define some steps. So what are the inputs of this? If I'm trying to convert this into a Boolean a combinational circuit, what's the inputs of this? So my function is this guy here. So I'm trying to discover what's the value of G7, and what we're gonna see is that the variables here inside the function are the inputs. So A and B in this case, B and A here. So those are the inputs of my function, of my combinational circuit. So every variable is gonna be the inputs, because we're gonna change that. Okay, so sometimes this is gonna be 0, this is gonna be 1, this is gonna be 0, this is gonna be 1. It depends on the time of your execution, and that's gonna provide what's the output required to represent G7 behavior. So variables, they're gonna be the inputs of your combinational circuit. So A, B, C in, or whatever names that you label, those variables are going to be the inputs, and the operators usually are going to be the gates. Of course that you can have sub-circuits, but if you have an equation like this, for example, I have and here, I have the complement of this function, I have complement of A, complement of B. Those are just gates that you're going to use to represent this variable in this form here, that the complement. And in this case, we have an exclusive OR here as well. And the function is the output. So G7 in this case is going to be the output of this function, and can be like Y or C out, any name that you give to your output here. It's the output of your function. So in this case, let's see. Let's just start from the inside the parentheses here. So here we have an AND, a complement of A and B. So if we're going to describe this in a digital circuit, in a combinational circuit, we're going to represent this with a AND gate, right? So you can see here that we have an AND gate, and it's complement of A coming from this node here, and B coming from this node here. So you can see that the line is crossed here. That's really common, but the fact that we don't have a circle, I think I mentioned that in another lecture. So the fact that we don't have a circle here means that those lines should not touch each other. It's not a connection here. It's just they are over each other. It's like two wires over each other, and they are not like connection. There's no connection here. So you can see that this part here we can represent as A. Does not take in account right now this complement over the equation. Just this part is complement of A and B, and so that solves this part. And the other part here is complement of B that comes from here, and A that comes from there, and there is the AND gate here that represents this part of the equation. And now for the rest of it, we have the exclusive OR, that's this function, but in this case we have a complement of all over all the equation. So it's actually exclusive NOR. We could have like a exclusive OR here, and another gate here that represents the NOT. That's going to be the same behavior. That's going to represent the same function. So, and that's that's the output. So that's the G7 output that we need here. So again, so that's the complete one version of this equation here that we can represent this way. So another one. So in this case, we have two outputs. How can we represent when you have more than one output? for our system. So again, the variables here, a, b, c, c in, those are the inputs of my. Those variables can have 0 or 1 to represent that state, that time that we want to provide to the circuit. And you can see that C is in this case, this is the carry out function, and this is the sum function. And again, the operators inside here are the gates that we're gonna build our system. So actually, this is a full adder. This equation represents a full adder that we're gonna use later in this course. We don't have to memorize this right now, but this is just how do you you have the addition of 2 bits with the carry in, with the output of the sum of those 2 bits with the carry out, so you can move it forward and have like 8 bits, 12 bits, 16 bits additions of bigger numbers. You start with just 2 bits, summing 2 bits, and the carrying, of course, because we need the extra bit here to sum, and you can have the output of 1 bit of that sum, and we put it together several bits, and we have the addition. So you can see that we use exclusive OR, we use OR gates here that we required. So it's the same in the same way that we did before here, from step by step, looking into the small operations, and we can see, for example, A exclusive OR B is right here. So you have B, you have exclusive A, and we have the exclusive OR operation. And in this case, we have AND. From this output, we have this guy here, AND with C in that comes from here. And we also use the same gate to another exclusive OR operation. So this exclusive OR, it's another operation to another function as well, right? So we're just using, instead of having totally different, so this operation is already done. So I can see here that A exclusive OR it's done. So I'm just gonna use the same output for this equation here. So that's what's happening. So I'm using at the same time to do this AND with C in, and I'm doing exclusive OR with C in, so I can provide the same output at the same time to both operations. It's faster, it's save resources, so save gates. It's a good idea to reuse when you have the same circuit. So you could close this guy here in a box, and you have 3 inputs, 2 outputs, and it's your full adder. So next class we're gonna see Boolean algebra. How can we see those equations and know which rules and which identities we can use to simplify them? Because it's the digital circuits are expensive. Sometimes you have to buy gates, you have to mount them on PCBs, and that's expensive. And if you have a smaller equation that represents the same function, it's cheaper because you're gonna use less gates. It's easy to see that you're gonna use less gates. Sometimes you just you want to reduce the timing, so the equation is too big, so it's gonna increase the delay of your system. That's another reason that you want to simplify your equations before implementing that on circuits. So that's it for today. See you in the next class. Thank you.